Our next speaker, Tomasz Włostowski, is a member of the Kicad lead development team. He is also a electronics engineer for CERN, where he designs circuit boards that peer into the heart of the universe and reveal secrets unknown to mankind previously. So please give a warm welcome for Tomasz.
Yes, good afternoon, everybody. Thank you, Seth, for a rock star level introduction. I probably don't deserve it. So, yeah, my apologies if this presentation will be a bit disorganized. I will try to show you a few features of Kicad and a few workflows that might be beneficial for designing something a bit more complex in Kicad. I don't think I have enough material for like full 40 minutes, so we can turn it later on after the slides into some sort of a Q&A session. Yeah, so recently I designed a rather complex PCB in Kicad. Being a Kicad developer since, it's been 12 years already, I think. We started in 2012 with Orson. I had been doing PCBs for much longer, since, let's say, the beginning of this millennium. I started with simple things as a kid in the high school, and since I started working at CERN many years ago, I moved to a bit more complex stuff with quite a lot. Oh, sorry. Thought it's a bit more sensitive. Otherwise, you can give me a bit more gain. Yeah, so PCB layout and hardware designs, my daily bread. I've been doing it for the past 15 years at CERN. These are mostly FPGA and mixed signal designs, data acquisitions, a little bit of RF design as well. And so far, most of this complex work-related stuff I had done using proprietary tools. I will not quote the name. But it rhymes with the key that you use for diacritic characters, at least in Polish, on your keyboard. So I met people in the past who did really extremely fancy stuff in Kicad for years. I saw really stunningly complex PCBs done in Kicad 4. Respect to the people who did that, because it required really excellent planning and a lot of patience. So I decided, and I convinced my colleagues to go full steam on Kicad with a bit more complex project. And we had some surprising results. So this is our guinea pig. It's called WREN, like the bird. Stands for White Rabbit Event Node. In our CERN world, it's what we call a timing receiver. So it's an essential tool for controlling a particle accelerator. When you have a beam of particles traveling pretty much at the speed of light, this is what at least happens in our bigger accelerators, the SPS 8 kilometers and the LHC 27 kilometers. The particles move at pretty much c. So they are faster than the light in a fiber and faster than any electrical signal in a cable, because they propagate with slightly less. In a typical optical fiber, it's like 2/3 of c. So we cannot really do a classical feedback control, like observe something happening with the beam, process, and then react, right? Because the beam will not be there anymore. We can only plan actions in advance. Right? We say, okay, so we turn on this magnet at half a second past midnight, and we activate the kicker 12.5 nanoseconds later, right? So in order to do that, we need a pretty well synchronized network that spans several kilometers. We have like fiber links of 15 to 20 kilometers all across the all across our campus, and the synchronization accuracy requirements are less than 1 nanosecond. In some extreme cases, like driving radio frequency systems, is like 10, 20 picoseconds. So this is the main purpose of that board. It receives commands and time of day information over an optical Ethernet link, and then produces pulse patterns exactly when we want them, and in all the places at the very same moment, if we desire this. On the more electronic side, it's based on a zinc ultrascale system on chip, 0.8 millimeter, pretty much fine pitch FPGA, almost 1,000 pins, with a DDR4 memory and almost fully found out programmable logic part, which also puts a bit of extra constraints on the PCB density. It has a ton of IOs. Because our clients, we are going to deploy at least 500 of these boards throughout our accelerator complex in the coming years. And our clients never know what they want. So we can only over-design slightly our boards. So here we have 32 bidirectional, 32 unidirectional, 50 ohm drivers and inputs with programmable termination, protection, and whatnot. Also some very machine-specific interfaces like interlocks, like beam instrumentation interface, etc. It has a bit of high-speed connectivity, gigabit Ethernet, also with the possibility of 10 gigabits. It can also be controlled over a PCI Express Gen 2.3 link, over a fiber, over an SFF 8644 connector, doubling as a VME. Yes, we still use VME computer. So the board has 12 layers with a bit of impedance control. It's not super tight because this is a digital design. It's not, let's say, 50 gigahertz range RF. That contains 6 pure signal layers, 2 hybrid power signal, 4 power layers. And really no fancy stuff like buried bias or high-end pad or any crazy features affecting the manufacturability and the price. We need to make this board cheap and in volume. So, what do you do before you start designing such a PCB? Think ahead. These things cost. It's maybe it's not like, you know, the cost of taping out a chip, but let's say if you want such a design as the one that I showed you on the picture, prototyped reasonably fast, let's say in 3 weeks, should prepare like 6,000 euros, not counting the BOM, just for the PCB manufacturing and assembly. So plan ahead, because mistakes at some point become expensive. This is not a $10 PCB that, well, if you reverse the layers or made a short circuit on the internal layers, you would throw away, right? It requires a bit of planning ahead. So first, go to your PCB fab and whoever will be assembling that PCB. Ask them about their internal design rules. Ask about their tips and tricks. Whole aspect ratio, for instance. Or courtyard clearances around the components so that they can inspect the PCB after the assembly. Do it before you start designing. Establish the design rules and make sure, do that first, make sure your PCB fab is aware of them and is capable of manufacturing the thing. Because changing, in particular, clearances or the stack up of the PCB with impedance matched tracks, once it's routed, it's a real pain in the neck. Then place the connectors, place the power-hungry chips in particular. Make sure you have enough clearances and space for everything else around them. Why this is important? Power planes and power integrity in general. The example of the zinc ultrascale chip that is on that board, well, this is a small one ZU4, so it's not that this much of a power hog, but let's say bigger zincs, they can easily eat 50 amps from a 0.8 or 0.85 volt power rail. And this is a bit, and some of these chips are pretty big, like 6 by 6 centimeter, 2000 plus pins BGA. So now imagine if you have a bit of a voltage dropout over your internal power plane. Let it be a modest 100 millivolts. 100 millivolts times 50 amps means 5 watts of power distributed across the bonding to your chip. This can simply evaporate it soon after the board is connected. And in my experience, power integrity is the trickier part, actually, when designing complex board than the signal integrity as far as digital mixed signal design is concerned. Most chips, in particular modern transceivers or memory controllers, are pretty lenient when it comes to slight impedance mismatch or spread in the routing delays. Power is a bit less forgiving. Develop a habit for running the DRC. For boards of medium to high complexity, 0 DRC errors and warnings, period, before you tape it out. And be prepared to get your first prototype with bugs. They happen. So since you are going to spend a lot of money on your prototyping, at least make sure you won't end up with a short circuit on the inner layers, like VCC to ground. And when you fan out your chips, try your best to have some space for workarounds, for wire modding, because doing this on the inner layers of the PCB, yes, it is possible, but it also costs. All right, so what Kicad has to do with it has a few, let's say, old features that are not very exposed and not very well debugged, a few new features that happened during the design of the WREN board, and a few ugly things that I personally discovered. So I take it as trying my own medicine a bit. I had been doing Kicad development for many years, but this is actually a first board of this level of complexity that we designed with a colleague of mine, pretty much completely in Kicad. Part of the schematics and one power converter was imported from Altium. So I'll talk about a few features that with a demo that became very beneficial for this project, like multichannel design, multidrag, a bit more advanced design rules. Also the état de hauteur, which is a bit, it needs a bit of care, and my subjective conclusions on the subject. So, as I mentioned, we have 2 times 32 identical I/O drivers in that board, and I would not like to design, route them, place them, all of them, one by hand. So, thanks to XKCD, there is a graphical comment. Instead of doing a boring, repetitive job, I'd rather write a feature for Kicad, which is called Multichannel tool. So basically, it's a smarter copy and paste that is aware of the hierarchical sheet instances and can map them into rule areas onto the PCB, so that you would design just one and automatically, or well, semi-automatically, repeat the layout to the other. Then if you change the reference area, you can repeat again, and everything will be updated more or less automatically. This feature is available, by the way, in the nightly builds already. You need to enable it in the advanced config. Check the documentation for that. Beware, it changes the file format. So if you add some multi-channel areas, older version of Kicad, including this table, will not read it. Oh, I forgot. I promised a demo. It's open. Oh, that's just my development version. So Yes, it will probably assert. As I said, I'm tasting my own medicine. So let's go to the most repetitive piece of the layout. It's actually a nested multi-channel design. So we have 4 blocks, 8 I/O drivers each, which consists, inside you have another 4 blocks, each implementing 2 I/O drivers. Oh, we have some issue with the arc rendering in the yesterday master. It looks good on this table, the transistor. So I would like to design this part once and have it automatically repeated on the PCB. So I deliberately broke it because this PCB has been fully routed already. Let's say this will be our reference channel, and we would like to arrange these components and route them automatically to do 3 other channels. So what do? Tools, multi-channel, generate placement rule areas. A rule area is something, it's a polygon on the PCB that you can use as a keep out, or you can use it as a sort of a holder for a bunch of components. You can define it either using a design rule expression or with this shortcut, generate rule areas, which will do it for you. Just choose the sheet instances in your schematics you want the rule areas for to be made. And there we go. So here is our rule area for channel 1, channel 2, channel 3. There is an option to group the rule area with the components, so that you can move it all together. This greatly simplifies placing things on your PCB. And then in order to duplicate the layout, select the master, the reference, whatever you call it, tools, multi-channel, repeat layout. It will automatically detect the rule areas that are compatible with your reference area. What does it mean that they are compatible? That they have the same connection topology and same footprints. They need not be in the first place within different hierarchical sheets, although this is the preferred way to go, because for complex multi-channel stuff, hierarchical sheet instances are generally a comfortable way of managing the complexity, right? So here there is a few options like enabling to copy the placement, the routing, grouping the components together with the rule area so that you can easily move this stuff with its local routing. A few others. Well, let's see what happens. It froze. Yeah, it's a debug version, so it takes its time. And we have our 3 areas copied and pasted. You can just now locate them in their final place and do the relatively simple task of assigning the connections fanning out from each of such channels to their final connections and the internal routing of the PCB. So this is already in the nightlies, and we are polishing up the user interface for it. Hopefully, well, this will be available in V9 as a first-class tool. Then what's next? That was actually the thing that I found missing the most, maybe not the most, but one of the, let's say, more annoying things while doing a complex layout. It's the lack of multidrag in the router. Simply grouping a few tracks and routing them as a bundle, moving them as a bundle. Yeah, you can use the show functionality to as a sort of a workaround, but it's not as streamlined as just being able to select a bunch of tracks and or vias and move them, keeping their a relative topology and the relative distances. So this is in progress. We'll show and walk around. It surprisingly took quite a substantial effort. Had to rewrite a major part of the show algorithm. So I can show you a sneak peek of this feature. I hope Kicad will not crash because, no, quite frankly, this is something that I'm really developing over the course of the past few days, or maybe few weeks. Okay, let's. Where do we have a lot of traces? Let's say we remove this, or route interactive router settings. Yeah, let's go to highlight collisions. Show is not there yet. So this is dragging multiple traces. We can also drag by the corner, and this already doubles as a, let's say, simple multi-route capability, because by repetitively pressing the D shortcut, yes, you see there are some rough edges, right? So this is coming in V9 as well, and hopefully it will make your complex PCBs, not only complex but simple ones, easier to design. What's next? So boards with FPGAs, with high-speed memory interfaces, they usually use DDR3, DDR4, DDR5. This requires a bit of signal integrity, in particular length tuning. Not as hardcore as many people would imagine, like length matching down to 0.01 millimeters is futile, but let's say plus minus few millimeters is a desirable goal. So Kicad already sorts of supports complex length tuning, although it's not exposed very well in the user interface. Hopefully this will be better in V9. You can fiddle around with it already in the 90s. The trick is to use the from-to function in the design rule language. If you imagine you want to define on the same track multiple routing paths. So in our case, we have two DDR4 chips, each 16 bits connected to the FPGA PLDDR controller, but we need to constrain two paths for the CMD because these are routed in a flow-through topology. So one address or a command pin is driving multiple address or command pins in different chips. So we want the electrical distance from here to here to be constrained, and also from here to there to be constrained. I would not like to constrain this part because there are stubs that also have non-zero lengths, right? All I care about is the distance between a driver pin and the target pin. Well, there is also a small stub here for the 50 ohm termination, but its length is irrelevant in this case. So how do we do it? We use the from-to function. So our FPGA is IC51. Our DDR chips are either 28 or 37. We create first a net class to group the control pins of the DDR in the board setup. So DDR4 CMD contains all the address pins, bank address pins, column address strobe, row address strobe, etc. Like in every other DDR memory. It's just an umbrella for grouping signals. And then the crucial part is the from-to. So we define it as IC51 ***, which indicates all pins that match the wildcard, and the target is IC28. So this call will basically extract all the paths between these chips that are topologically between the pins of IC51, IC28. So means the whole path from this pin to this pin will be taken in the account. Whereas the second rule constrains only the path between 51 and 37. So the length tuner will take into account only this part. I'm not sure this will work well in a development version of Kicad because I might have broken something, but nonetheless, let's have a look. Custom rules. Yeah, so this is our rule. Let's say our target is 43.5 millimeter. No, 43 with plus minus half a millimeter tolerance. Let's see what the DRC will tell us. Nope, we are out of range. But the rule only took into the account the respective chips and signals, so only the control bus of the DDR. In this way, you can carefully choose, constrain particular signals, particular signal groups in order to meet your routing requirements. There is a few more on this board. So there is one. There are two for the address because we have two chips, and we have 4 additional rules matching the lengths within each byte group. So in a typical DDR4 controller, you can have a different length for the control bus, as long as the difference fits within, let's say, half of a clock cycle. And each byte group can have a different length. This greatly simplifies routing, but nonetheless, you have to align them within each group. So this is a complete set of rules for 2 DDR4 chips. What's next? As far as more advanced DRC is concerned, you can do per layer and per class impedance. If a board has a complex stack-up, well, it's not to be complex. If you have differential routing on the inner layers and the outer layers, the dimensions are likely different because the outer differential pairs are microstrip, the inner ones are strip line. So you can do that in Kicad, but defined in terms of geometrical dimensions and not in terms of impedance. You cannot say I want a 50 ohm trace. Some people might complain about it. I personally take it as an advantage because my experience with various field solvers and signal integrity calculators shows that they differ by plus minus 30%. So it's better to just to make to come up with just the dimensions instead of relying on yet another tool being reliable. Plus, add a bit of manufacturer overhead on that. So here we have an example for with differential pair gap and maximum couple length for the outer layers and for the inner layers. We only have 100 ohm differential pairs in this project. So it's pretty simple, no net classes or other filtering involved. Okay, last section is a bit personal for me. Yeah, many people have been ranting about the router. I joined that team of complainers. Yes, I will also rant about in large part my own stuff. Yes, the router became subtly worse. I've heard people saying that in V7 it was smoother. In V8 it's not as smooth. There were many issues under the hood that we are trying to address. First of all, a router assumes almost exact geometric computation. It's all based on fixed points where all the rounding errors are assumed to be bounded to plus minus half an LSB. So a point, imagine you calculate an intersection point between two line segments. We assume that it lies on these segments when it's not further than half an LSB away from the actual intersection point, which might not be integer, right? Fixed point math isn't easy, and the geometry library is used throughout the entire Kicad. It's not like only the thing for the router. So as people add new features, fix existing bugs, they might introduce issues as well. And quite frankly, the REN board was an eye-opener for myself that, yeah, the router needs a bit of extra care. And I honestly admit I had a bit less time and energy to work on it over the past few years. Hopefully I will find a bit of motivation now. But it all boils down to automation of tests, regression tests, so that if somebody introduces some possibly harmless or harmless-looking change in the geometry code, it won't affect the router by changing the bounds of the rounding error. But on the other hand, how to test an interactive tool? It's almost like testing a game, right? It must have the right feel. Designing your PCB almost feels like a quest, right? So shall we? I don't think we have the budget or the resources to test it like, you know, they test games. We can only try to make regression test cases. I will talk about them a bit later. Okay, I also noticed another big source of, let's say, hiccups of the router, which is caused by tiny, dirty things in your tracks, tiny overlapping segments, tiny junctions that have like a one teeny-weeny little stub somewhere in the middle. The way the router works is it requires clean traces that end perfectly on pad anchor points or Y anchor points, without any doubled segments, overlaid segments, etc. So I started working on something called pre-route cleanup, which will automatically remove this sort of issues, hopefully making the routing experience way smoother. Another issue with the VME REN board is we have per board area clearance rules. That means the width and clearance under the dense BGAs, the FPGA and the DDR chips, is is a bit narrower than elsewhere. So this unfortunately caused quite a bit of performance issues with the router. And I have a few ideas how to optimize it, but this will come at a trade-off in accuracy. I mean, you might get slight inconsistencies between the DRC and the router, but as I mentioned at the beginning of the presentation, always run DRC. The router is your aid. It's supposed to help you. It's not meant to ensure your PCB will be according to the rules. Yeah, and last but not least, actually, this was probably the only thing I really swore about loudly, is differential pair routing, in particular lack of differential pair rework. This means dragging them as a whole and being able to start to reroute an already existing differential pair without deleting the already routed segments. So yeah, I hope this will be fixed soon. So to summarize, what was bad? What made my experience bad in the sense that lowered the most my productivity? Differential pairs definitely on the first place. Multidrag, I could live without it, but it would save me a lot of time if I had it. And router hiccuping. So basically, mostly my own fault. The ugly stuff that requires also a bit of care. We need a proper test suite for the router. Let's say there was some groundwork done. Wayne mentioned during his presentation on bug reporting that there is this regression testing tool and the bug TNS debugger tool. It has a bit of rough edges. Hopefully it will become a bit more maintained. Just a note, if you'll see any regression in the router, when you create these dumps with the 0 key, if you could, make two. One with a working version of Kicad and one with the version that misbehaves. This will let us react and fix the bug and analyze it much faster. Yeah, also length tuner and DRC checks. This is undocumented and with a bit of an obscure interface. Well, to not end this with negative thoughts, it took roughly 6 weeks to design this board, including 2 weeks to develop like a basic multi-channel tool. During that time, I had 3 or maybe 4 crashes, and I was running a development version. That's not bad, I would say. My conclusion is whatever Kicad misses in terms of features, because really this is a pretty complex board, over 2,000 components, 12 layers, constrained lengths, pretty dense routing. Whatever Kicad missed in terms of features, it compensated with speed. One very notable example is Kicad doesn't have a dedicated pin swapper. And I didn't feel like I needed it, even though I had like 300 FPGA PL pins to swap. Because switching from schematic, from PCB to the schematic is a fraction of a second. Moving a few labels around is a fraction of a second. Updating the PCB, again, to annotate the changes is maybe 2-3 seconds. That's like this. Our competition that I used for many other designs takes 2 minutes to roughly to back annotate the schematic changes to the PCB. Yeah. Yeah, hence the 10 dB gain roughly in terms of speed of stability. Thank you very much. If you have any questions, we'll be happy to answer them.
So with respect to the multi-channel tool, there used to be a plugin that did mostly the same thing, the replicate layout plugin. Can you comment on the difference? Or?
I'm afraid I did not understand your question. Could you?
Mitya had a replicate layout plugin that did similar things to the channels you demonstrated at the beginning.
Did I mention that I hate Python?
It came up once or twice.
No, quite frankly, I felt like this is an essential feature. It must be integrated into the tool. Let's say I envision plugins as something that makes Kicad or any other software tool more tailored to your personal needs. If you need fancy documentation, if you need to generate some super specific PCB features, yes, this is the way to go. But honestly, place of a multi-channel tool is as a core element of every layout program.
Okay, I have the microphone now. Again, thanks a lot for the amount of work you put into it. It's really great to see. I have one comment on the block layout thing. I've worked on a couple of designs, and I'm one of those guys who really don't like hierarchical designs. I've seen, one page explode into 3, like a memory interface going from 5 pages to 26 pages because people are adding so many layers and signals. And of course, doesn't matter how you do it, but would you consider, I don't know if it's feasible in that particular situation, when new features are added, that they're not dependent on the hierarchical blocks?
Yeah, I think there is no like hard-coded dependency on hierarchical blocks. It's just my workflow. But James from our dev team, I think he's working on basically putting like blanket rule areas on the schematic level. So you can put like a polygon around a bunch of components and attach it to a placement rule area. And this way, you should be able to use the multi-channel tool with that. No, I think he was also doing something like really like a rule area, but on the schematic. Yeah. Or maybe I should discuss this with him or in more detail. Yeah, but yes, this is not bound to hierarchical sheets.
First of all, you definitely need to route more boards if that means you design such features.
Thank you.
Keep it up. So the multi-channel thing, if you update the reference, does it automatically update the further ones, or do you need to rerun the tool?
No, you must update. You must trigger the update process manually.
Okay. Then second question, it said the router is kind of lagging behind because you didn't have any time or energy for it.
More or less.
Is that still the case, if I may ask?
That's more or less the case.
Okay, thank you very much, Tom.
Thank you.